That's okay. I'll have time to grade it later. But if I close out Canvas, then all my comments that I've made so far get lost. So I'll have to look at it again and make comments. Anyway, what we see today, what we're getting into today is discrete probability. And what you see here are some of the ideas that we have when it comes to that sort of thing. We've been counting sets, and one of the reasons we do that is because we're trying to figure out what's the likelihood of things happening, or how can we analyze populations to determine what sorts of things are going on. Can we extrapolate from a sample size that we take, and what can we determine from that? So those are all things that we actually look at here. And a lot of it is based just on data collection. So as an example, in the upper left-hand corner is just a look at a set of how many major changes are made in something. We don't even know what it is. And it's just counting. There's 1, 2, 3, or some number of changes, and then we assign a probability based on those numbers, and with the idea that our probability is going to end up equaling 1 no matter what. We have kind of the same thing for graph A, graph B, graph C, and graph D there, each one of them indicating some kind of distribution in terms of the likelihood of certain events happening. We also have a conditional probability definition on the right-hand side. We're going to get into that a little bit more. It's just one of those things where we have to determine whether or not two events are independent, whether they depend on each other, what are the kinds of things that influence that, and how can we measure it. So let's get going here. Oops. I was in OBS. There we go. So we'll have a quick review. We've been talking about counting. Now we're going to look at what we need counting for. We'll talk about probability distributions in general. One of the things that we've been looking at, or that I talked about last week when we talked about probability, was whether or not things were equally likely. There are, of course, other instances where they are not, and we have to be able to handle that. And then Bernoulli trials are one of the main things that we're going to get into. We're going to be using the Bernoulli trials in the next programming assignment. One of the main reasons we count is discrete probability. We have to determine what kinds of things are possible if I have a certain set of outcomes. What's the likelihood that you're going to get into, that any of us is going to get into an accident on any given day? Well, the way we figure that out is by counting how many people are driving, how many people get into accidents per day, and you might have that by state, you might have that by the United States, you might have it in the world. And we use the data that we collect to determine some kind of probability that says, what's the likelihood of getting struck by lightning? Well, that's based on how many lightning strikes we think there have been and how many people have been struck by lightning during particular years. So we count in order to determine that. What's the likelihood of winning the lottery? Well, that's another one that is based on counting. So it's not always bad things that we're looking at. There are some good things that we look at, and we determine a probability based on that. A lot of the things that we look at are based on the idea that everything is equally likely, that we have this even outcome. I have a fair coin. I have a fair die. Everything is exactly the same when you leave the building here. Your probability of something happening is exactly the same as anybody else's, and we make that assumption in many ways, in many times in life. Sometimes it may be a really good assumption. It's something that's really indicative of reality. At other times, we may discover that our idea that we have an equally likely probability for each outcome is not necessarily the same thing. But the likelihoods associated with some idea of fairness of what's going on. If, for example, you do buy a lottery ticket, the idea is that your lottery ticket is equally likely to win as anybody else's lottery ticket. That there is no magic that somebody can do to make it so that their ticket is more likely to win than yours. So the likelihood is one of the things that we talk about, and we use that in counting. In general, when we count, we're assuming that there's an equal likelihood for most things. So we'll assume all outcomes are equally likely, as opposed to talking about some different probability distribution, and we'll press on from there. So we're considering sets, or the events that we have, and the sets of outcomes that we could possibly have, and saying what sorts of things are there. When we talk about probability, we're talking about the probability of an event occurring. What's the probability of an asteroid striking the planet? Well, it's happened once or twice. But the idea is that if I have some set of possible outcomes, like rolling a die, some set of outcomes for a six-sided die would be 1 through 6, then the event would be some subset of the set 1 through 6. It could be the numbers 1 through 5. And I could say that the probability of rolling something other than a 6 is, and it's given by the formula of the cardinality of that event, the elements in that event, divided by the cardinality of all possible outcomes that are there. So the probability, and once again, the probability of all possible outcomes occurring, yeah, it's 1. That is, something's going to happen. We're going to have one of the results, otherwise we wouldn't even be talking about this sort of thing. So we define our set as the set of all possible outcomes, and one of the outcomes is going to happen no matter what. So the probability of one outcome happening is always given as 1. The probability of rolling a number greater than 4 with a six-sided die, each side number 1 through 6. Well, if we put that in here, we'll have the probability of the cardinality of the set of numbers that are greater than 4 on a six-sided die. What's the cardinality of that set? 2. Yeah, the numbers 5 and 6. Divided by the cardinality of the entire set, which would be 6. So 2 such outcomes, 5 and 6, total outcomes are 6. So we have a probability there that would be 1/3. For an even roll, man, how long have I had even roll in there? You ever have one of those days where you look at things that you've had out for a long time and suddenly it's just not right? So our probability here for a roll greater than 4 would then be 2 divided by 6, which is 1/3. One thing to note, normally we express a probability as a fraction. In popular usage, you'll often see them expressed as a percentage, where a percentage is nothing more than a fraction expressed as a hundredths, which you undoubtedly know. So the probability of not an event would be what? Well, if we know the probability of the event, then we can figure out the probability of anything other than that happening as being 1 minus that probability. So it's the cardinality of the entire set minus the elements that are in the event E, and then divide that by the cardinality of the set. And I did some highlighting the other day, and I missed the letter S here. The sum of the probabilities of all possible results, as we just said, is 1. It just means that every time you run a trial, something's got to happen. When we flip a coin, we say that the possible results are heads or tails. If you lose the coin, then you didn't actually flip it, you lost it. So that would then mean that we didn't have the trial at that point. But that allows us to talk about the probabilities in a realistic way in terms of counting. When it comes to counting sets, we also have the idea that we may have intersections of things happening or other kinds of things going on, and we have to be able to talk about that. So if, for example, I have two events, E1 and E2, then if I want to look at the probability of one or the other event happening, I have to be able to count how many elements are in that. And as we saw before, when it comes to counting, then I have to be able to count how many elements are in set E plus how many elements are in set E1, or how many elements are in set E2, and then I have to be able to subtract the number of elements in E3, or pardon me, in their intersection in order to get the actual probability there. And we find that those formulas actually work for us. So we've talked so far about every element having an equally likely outcome. What's that called? Anybody know? You guys required to take a statistics class anymore? I mean, my comp sci days, my undergraduate comp sci days are a little bit behind me. I took them in an engineering college too, where we had to go through, I don't remember if we had to go through differential equations for comp sci. I was an engineering physics major at first. So we had to go through differential equations, but then statistics was required, because a lot of the things that you do, you end up doing statistical analysis of the particular results. But if everything is equally likely, what we call that is a uniform distribution. In other words, everything is uniformly probable. It's the same. So that would be a uniform distribution. Have you ever heard of any other kind of probability? Have you taken standardized, well, you probably did take a standardized test to get in here. So one of the things that they talk about in standardized tests is the type of distribution that you have. And normally what you have is you have a mean here, and that's not a bad person. It's simply the average of values. And what they say is that in general, the population, everything else, looks like a normal distribution. It's also been a long time since my last statistics class, so there are a couple of things that I probably won't be able to define perfectly for you here, but we have what's called a standard deviation. Sigma minus sigma plus sigma. And what we say is that that is a measure of how spread out the distribution is around the mean. So if I have a fairly large standard deviation, that means that I have a fairly flat curve there. And if I have a really small standard deviation, that means most of the things that I'm looking at are going to be in the middle there. And then we've got plus 2 standard deviations and minus 2 standard deviations. This I do remember. Sigma is standard deviation. We call mu is the mean, average. And then what we know is that 5% is above 2 standard deviation and 5% is below -2 standard deviations from the mean. So for a human population, this is what you normally see when it comes to heights of individuals, when it comes to heights, weights, IQs, scoring on exams, other stuff like that. All of that is determined by the mean that you measure and then the measure that you have of what the variation is in the values, which is what the standard deviation is. So that's how they arrive at things like your percentile rank and everything else. It shows somebody where you would be on the curve and what kinds of things are there. We could do the same thing with, sizes of dogs. Since I have a 100-pound plus dog at home, you could say, where does a 110-pound dog fit in the measurement, the distribution of dogs? Is that the average? No, Chihuahuas don't come anywhere close to that. In fact, there are a lot of breeds that are much smaller than that. So we're probably talking at that point as a dog at the top end of the size distribution for dogs. And all this really means is that the probability of somebody being at a specific point in this distribution, so the probability of being here, probability of, let's say that I've got a set of events here, probability of E is going to be given by some measure of the curve and everything else. It just means that it's more likely that somebody's going to be within one standard deviation than it is that they're going to be more than one standard deviation out. And the normal curve is not the only one. The student t-test is another one. There are all kinds of distributions out there. The two most common ones that we'll come across, though, are either, at least with discrete probability, the most common one you come across is the uniform distribution, but there are other ones out there. It just means that the probability of any given event is not necessarily going to be equal in all cases. So it's more likely for somebody to come close to the average. Like if you look at the heights of individuals, you'll find most people are kind of clustered around the average height for individuals on the planet. So the probability that somebody is 5'9" is much higher than the probability that somebody is 6'9". And that's simply because 5'9" is the average height for, at least for males in the U.S. I'm not sure if it's worldwide, but I know it's the U.S. So 5'9" is the average. It's more likely that somebody you bump into on the street that's male is going to be closer to that than it is that they're going to be, like, what is it, Wembanyama, the new San Antonio Spurs player that's 7'3" or 7 foot something, and has arms that are 10 feet across or something like that. My son's we lived in San Antonio, and my son's a San Antonio Spurs fan. So he watches that closely. I just kind of, the Spurs, whatever. It's like the Jazz, yeah, whatever. I know they play. Karl Malone doesn't play for him anymore. He has an automobile dealership. And John Stockton, I don't know where he is right now. But my basketball days are, I left it in 6th grade seventh grade because I was just too short. Haven't played basketball a lot since then. At least not organized basketball. I did play in college in intramurals. Do they have an intramural program here? I never really thought to ask about it. I mean, on a lot of campuses where there's a larger on-campus population, intramurals is popular. So we had 3 dorms and like 7 fraternities and 8 sororities on my undergrad campus, and so intramurals were fun and they were very competitive for a lot of different things. But the idea also when it comes to the probability is that if I sum the probability of all the different things, discrete things inside of here, that the probability summation would still be 1. So it doesn't matter what the distribution is. it will always end up that the probability of all possible outcomes of any the probability, the sum of the probabilities of all possible outcomes is always going to be 1. Okay, so even if the things don't have the individual events, the individual things don't have the same outcome. Let's take a quick look now at conditional probability. And conditional probability is also related to the idea of independence. Now, are two things independent? Now, what's the likelihood of you getting into an automobile accident? Well, it depends. Do you have a driver's license and own a car? You have a higher probability of getting into an accident if you have a driver's license and own a car than you do if neither one of those is true. So we want to look at the conditional probability of things. For example, events E and F. You want to look at what's the likelihood if you do have a car, F. What's the likelihood of you getting into an accident, E? And that would be one of the things that we would talk about here with the conditional probability. That may not be the type of thing that we're looking at, but let's say we can look at this as a way of saying whether or not there's something going on. Suppose event E is the event that there are an odd number of tails in 5 flips of a coin. And that F is the event that the first flip is a head. So in this particular case, we're assuming a fair coin. We could easily assume a non-fair coin. It would just change the probability of individual outcomes. So here we know that the probability of the first flip being a head is equal to 1/2 if I have a equally likely outcome. In other words, my outcomes are I have a head or I have a tail. We ignore the edge. When you flip the coin and it sticks into the potatoes, mashed potatoes, then maybe it could be on an edge, but we'll say that it's always leaning one way or the other slightly, so we'll call it a head or a tail. So then the question becomes, what's the probability of E intersect F? In other words, that there are a large number of, that we have an odd number of tails in 5 flips, and that the first flip is a head. Well, what are our possible outcomes? Odd number, let's see. So with 5, you'll have to bear with me, there are 32 possible outcomes here. Well, even if we ignore the first flip if the first flip is a tail, then we've got tails, 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 heads, tails, 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 heads, tails. You get the idea here. It becomes binary counting at this point. So sometimes it's hard to see what all the possibilities are without actually listing them. So tails, tails, heads, heads. Tails, tails, heads, 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 tails, can't count, tails, tails, heads, 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 tails, heads, tails, 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 heads, tails, tails, heads, tails, heads, tails, heads, tails, tails, heads, tails, heads, heads, tails, heads, tails, heads, tails, tails, heads, tails, heads, 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 tails, and tails, heads, tails, tails. Oh, pardon me. It's heads. 16 out to 16 there, and then the other one would just be, I've got a head, and tails. You get the idea. And that goes down to heads. So what we've got over here is let's mark our odd numbers of tails. Actually, I probably should write out the other ones as well, just to avoid confusion. Heads, tails, heads. Almost right. So I've got this new thing and trying to get it to be easy to write on. It's different, but I may not have to carry as much stuff, so that's always heads, tails, heads, heads. Yeah, I'm at about the same spot here, so we can go heads, tails, heads, tails, heads, tails, heads. I'll just write with the beaver state now at the bottom. Heads, tails, tails, heads, tails, tails. I can't even read this now. Heads, tails, and then heads. All right, so now we're going to mark them. So that's got 4. This one's got 3. That one's got 3. That one's got 3. That one's got 2. This one's got 3. That one's got 2, 2. I've got 1 here. I've got 3 here. So we're just marking all the ones with an odd number of tails. I've got 1 there, 2, 2, 1, and then we're done. So 1, 2, 3, 4, 5, 6, 7. If heads is the first one. And then over here I've got 5, 4, 4, 3, 4, 3, 3, 2, 4, 3, 3, 2, 3, 2, 2, 1. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. I'm missing one here. I must be, that one. There must be another one here. And that one. So I've got 16 total. So the cardinality of E is then equal to 16. Cardinality of S is equal to 32. What's the cardinality of, is an odd number of S? What's the cardinality of F?
Wouldn't it also be 16?
It's also going to be 16. So in this case, we're going to have the probability equal to 1/2 for F. We counted them over in the right here. So this is F. And then, pardon me. Let me write that in a different color because that F is 16 outcomes. And then the other one is E. E is equal to, or is 16 outcomes. So that's how we get our probabilities there. So we have the probability of F is 1/2, probability of E and F occurring at one point. So that would be the number of things here. This is E intersect F. Is that part right there? And so the probability of that, we've got 8 of them overall. So the cardinality of E intersect F is equal to 8. So that gives us our 1/4. And here, the conditional probability would then, in this case, equal the probability of intersection divided by the probability of the thing that we're conditioned on. In other words, the probability of an odd number of tails, given that the first flip is a head, is given by that formula, 1/4 over 1/2, which would be 2 divided by 4, which would equal 1/2. So that's our idea there. You might say, why are we going through this? Well, there are more interesting cases that so one of the things that we worry about, that we have to think about, is that because things are independent, we have a conditional probability that doesn't affect the probability of something else happening. In other words, just because I flip the coin and I have a head the first time, it doesn't change the fact that I can still, the probability or the likelihood that I have an odd number of tails. So the conditional probability forms the foundation for what we call independence. So the independence of something means that one event is independent of the other. The likelihood of being in a car accident is independent of the likelihood of you owning a car. Well, that's probably not true. So independence is something that we do want to look at in order to understand how likely different things happen to be. So if I have two events, E and F, we say that they're independent only if the probability of the intersection is equal to the probability of one given the probability of the other. So what we saw on the previous slide was that the probability of E intersect F was equal to 8 over 32. And the probability of E was equal to 1/2, and the probability F was equal to 1/2. And what that ended up meaning was, well, 8/32 seconds is 1/4. The question is, does that equal 1/2 times 1/2? And since it does, we would say that the probability of having an odd number of tails is independent of whether the first flip is a head or not. So that's the idea that we're trying to get here. Let's take a look at something that's a little different, and we'll say, okay, how can we actually use this? Suppose that a family has 4 children, with 4 children, has males and females, and that F is the event that there is at most one boy. In other words, there's 0 or 1 boy child within the family. So the event for the family with 4 children obviously means that, well, what could we have? We could have for all 16 possible values, we could have male, male. Well, that would be a lot of fun. All four boys. Well, actually, when they're teenagers, it would be a lot easier. Having three teenage girls. The youngest is a teenager officially as of 2 years ago. So yeah, it's been interesting. Male, female, male, female, female. That was my family growing up. My oldest is a sister, and then a brother, and another sister, and then me. Female, male, female, 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 female. Okay, so E is the event that a family with 4 children has males and females. So that means that we've got how many events here where there are both males and females? So there are, let's see if we can go through this in an organized way. 16 outcomes for 4 kids. So E is equal to all the stuff in the middle here. So where I have both males and females. E is equal to 16 outcomes, or pardon me, 14 outcomes. So then F is the event at most 1 boy. Well, where do we have at most 1 boy? So let's take a look at F. F is at most 1 boy. So that would be 0 or 1. Well, I've got 1 there, 1 there, 1 there, 1 up here. That's the only one that I've got in the first half. I believe so. So I've got 1, 2, 3, 4, 5. These 5 outcomes. So the S has 16 outcomes, 4 children, 16 outcomes. E is 14 of them, F is 5 of them. So then we look and we would say, where do they intersect? I'm almost out of colors here. So then E intersect F. Well, F is the dark blue, E is the green, so I've got 1, 2, 3, 4. So I've got 4 outcomes. So now we should just be able to plug the numbers in. So the probability of both boys and girls is 7/8. I have an easy way to get that out of my writing there. And the probability of at most one boy was the 5 cases that we talked about. So that would be 5/16. Repair it after the fact. That's the rule of the day. Oh, look, it worked very well. So now we've got 16 possibilities. We've got everything working out for us now. So we can say that the intersection is 4/16, 4 outcomes, or 1/4. The question is, if those are independent, then the probability of E times the probability of F will equal the probability of the intersection. And that's our question. Are they independent events that I have at most one boy and I've got both boys and males and females, boys and girls? Well, does 1/4 equal 5 times 7, or 5/16, so it would be 14 sixteenths, or 35 1/28ths, if I multiply those two numbers together. 35 1/28ths. If I multiply 7/8 times 5/16, 1/28, and then 1/4. If I multiply both the top and the bottom by 32, I get 32 1/28. So the question is, are these equal? And we see that they're not. So having at most one boy is not independent of having, let's see, F. So F is the event at most one boy. Given that we have at most one boy, 0 or 1 boys, is that independent of having both males and females? And the answer is no, it's not. So if I have both males and females, it changes the probability of having at most one boy. That's the whole idea here, is that given one condition changes the probability of the other condition. So it affects how likely it is that something's going to happen. And that's what makes an independent event. A couple of some terminology that I threw at you there. I threw at most at you. And I believe for the programming assignment, what I ask is at most, what's likely. Actually, I may have done two of them. There are two that are pretty much the same. So at most 3 means 3, or 2, or 1, or 0. At most means, well, that means I don't have any more than that. So 4 or more is not in play. But we're talking discrete events. And when we're counting, we start counting at, not at 1, 0. Because we could have 0. So that's the idea here, is if I say at most 3, that means 0, 1, 2, or 3. No more than. It means no more than. So if I say no more than 3, it's exactly the same as at most. I mean, the words are different, but it means the same thing. So no more than 2 would mean 0, 1, or 2. Not 3, because 3 is more than 2. So it's just like saying at most. The other one that we would probably have would be at least. So at least means, well, if I have at least 2, it's going to depend on how large my set is. So I have 32 results for one of those. So at most 2 then becomes a larger number that we can have to worry about. But the question is, if I'm looking at 100 things and I tell you at least 2, do I have to figure out, at least 2, do I have to figure out 2, 3, 4, 5, 6, so probabilities for each one of those? The answer is we cheat. Not really. We use the summation rule. We don't have to figure out 2, 3, 4, 5, 6, 7, 8, even if it's 10. That gives me 2, 3, 4, 5, 6, 7, 8, 9, 10. Gives me 9 things to figure out. I could do it by figuring 2 things out instead of 9. I like that. So we use the summation rule. We know that 0, 1, 2, up through all of the possible numbers or outcomes there is going to equal 1. That's correct. So what we do instead is we figure out 0 and 1. If I say at most up to n, then I figure out the smaller value and I subtract from 1. And that gives me the same answer. So the probability of at most, or pardon me, of at least 3 is the same as 1 minus the probability of no more than 2. So you have to be a little careful about what you do, otherwise you could end up doing a lot of extra work. Now let's take a look at something that is based on this idea of independence. So we have to be a little careful here because independence is something that is not necessarily something that we can just tell off the top of our head. But what we want is an experiment that has 2 possible outcomes. Yes or no. Yes, somebody has passed high school. No, they haven't. Yes, somebody weighs over 100 pounds. No, they don't. Yes, somebody is over the age of 20 or not. There are 2 possible outcomes. There could be a whole bunch of possible, or not outcomes, but categories, events. There could be a lot of things in that set of events, but we have to boil down to either yes or no or a 2 outcome case. So we can't have something like a score of 1, 2, or 3 because that won't work with Bernoulli trials. The other thing that we need is we need every outcome to be independent of the rest of them. And that's vitally important for being able to use this. This is the hammer that I give you guys, and I promise you that some of you will use the hammer on some screws that I give you. Those of you who have ever worked on with any kind of tools know that you do not hammer screws into wood or into anything else because a hammer is not the tool you use for screws. You use a screwdriver. So consider the screwdriver as a count where you count things manually and or using formulas, and the hammer as, oh, I got this one figured out, I'll just plug it into the formula. But we have a probability, a formula for determining exactly some number of outcomes if I have a given number of trials. So if I go out into Salt Lake City and I grab 100 people off the street, what's the likelihood of getting 25 of them who are declared independents? That would be a question we could answer with this. We'd have to know what the probability of any one person being an independent would be, but as long as I'm not going to the Republican convention in Salt Lake City, I'm probably going to be okay with just grabbing people at that point. So In other words, we're guaranteeing the independence of what's going on. So the probability of event 1 of the person being an independent is P. The probability of them not being an independent would be 1 minus that value, 1 minus P, we say that's Q. Then the probability of getting exactly 25 people out of the 100 is going to be given by this formula. Combinations of n things taken k at a time times the probability of k, that are p raised to the k and q raised to the n minus k. So let's take a look at an application. We'll have a couple of different applications of this. And Thursday we'll spend a little bit more time on it as well. Suppose the probability of somebody having AB positive blood is 0.04. This is close to accurate if you look at the little asterisks there. I've hidden the note down at the bottom. For the United States, it's actually 0.34. I made it 0.04 because 0.04 is easier to do the math in my head, and I don't have to run to my calculator quite as quickly. I'll still have to use the calculator, but not quite as quickly. So if we select 10 people randomly from the United States, what's the probability of having exactly 2 people with AB positive blood? That would be the kind of question that we could ask, where we'd say, all right, we're going into this area and we're going to test everybody, or we're going to test and we're going to see, do they follow the standard? If we get an answer different than what the Bernoulli trials would tell us, then we might make some other assumption about the population, for example. If I go into an area, let's say that we know one city in the United States has a high number, for whatever reason we had the AB pluses all moved there. So we have a city that is, it's 50% likely in that city, then we would have something different going on. And we could test that by going out and grabbing 10 people on the street. But the formula I have would be, what? Combinations of 10 people taken 2 at a time. So K, go back to my, I really wish they had just a different, so here we have N is equal to 10, that's the number of trials. K is equal to 2, the number of successes. S-U-C-C-E-S-S-E-S. Yeah, I got a C in spelling in 3rd grade. I was very upset with that. Not really. Not enough to change what's going on. But what we find when we plug this in, combinations of 10 things taken 2 at a time, it would be 10 factorial over 8 factorial divided by 2 would be 9 times 2, which would be 18. 18 times 0.04 raised, 0.04 squared, that would be 0.016 times, whatever. They're 0.016, and then whatever 0.96 raised to the 8th would be. But it gives us about a 5% chance. So if I go out randomly in the street and grab 10 people, I don't have a very high likelihood of getting 2 with AB positive blood. In fact, I have a very low probability of that. I would expect that I would have to do this experiment 20 times before I have one case where I have 2 people with AB positive blood. That's kind of what it's telling us here. So let's say that we do go into AB positive land, and we have a class, 20 people in a class, and we try the same thing. Now, for probability's sake, if 2 people have AB positive blood out of our 20 in the classroom, that's about the national average. You'll have either 1 or 2 on average, if that's the case. So what happens here? Well, one of the things that happens is can't use Bernoulli trials. We have the hammer, and now we're given the screw that we're supposed to affix or to put properly here. When I have small populations, what happens if I take one, if I know something about the population? For example, here I know that 0.1%, or 0.1, I have a probability of 0.1 of a single individual having AB positive blood. If I select one person, what happens? So if I select one person, the likelihood that that one person has AB positive blood is going to be 0.1. What if they have AB positive blood? What happens to selecting the next person? What's the likelihood that they have AB positive blood? It's no longer 0.1. What that means is, in a small population, sampling each individual trial that I take affects the probability of the next one. So by having a small population of 20 people and knowing that I have 2 people in there, the first person I take, let me do it with a board here. First person, 20 people. I don't remember if I I don't remember. I was going to say, I don't remember if I have this on the next slide or not. Oh, I have room for it. So, yeah. So I have to use counting. What this allows me to do is I actually can then put this. People can look at it and take notes from it and stuff like that. So I've got a room, 20 people. 2 have AB positive blood. So if I select one, the probability that person A has AB positive blood is 0.1, or 2 divided by 20. So the probability of getting one of those 2 people out of the 20 becomes 0.1. So probability A probability AB positive is 0.1. Okay, so one person. The person 1 has AB positive or not AB positive. Well, let's just put AB positive and not AB positive. So I won't put that. Yes, it has. So at that point, for person 2, what we find is that the probability of AB positive blood, well, if person 1 is AB positive, then it's equal to 1/19. If person 1 is not AB positive, then that's equal to 2/19. That's the probability that we have for the next person. If the person 1 is AB positive, then we have this whole thing for person 2 where I've got either a 1/19 chance or a 2/19 chance. And if person 1 is not AB positive, pardon me, if they are AB positive, then I've got a 1/19 chance of going that way, and an 18/19 chance of going this way. So, and over here I had a 0.1 or 1/10 and a 0.9 so going that way. If they're not AB positive, then that means over here I've got a 2/19, and the other way I've got a 17/19. And it keeps changing. Every person I draw, the probability of getting something is different. So, do we want to go through one person at a time and try and figure this out? No, we don't. So what we do is we count. Counting would be, let's see, so how many ways to select 10 from 20. Is order important? No. So we're talking about a set partition. They're either in the 10 we select or not. So this becomes combinations of 20 things taken 10 at a time. How many ways to select two people? I'm trying to remember what our problem is. We're trying to get what's the likelihood of 10 people and getting two of them, both people with AB positive blood. So how many ways to select two people from two? So I'm selecting all of the people with AB positive blood. In other words, all the AB positive. I've only got two, so two from two. It's combinations of two things, taken two at a time. And as you know, this is equal to 1. And then how many ways to select 8 people from my remaining, the 18 non-AB positive. Once again, order is not important, so combinations of 18 taken 8 at a time. So this becomes the probability of 2 people in a sample of 10 would be the combinations of 2 things taken 2 at a time. So the ways to do that times the ways to get the 8 people to go with them, 18 taken 8 at a time, divided by combinations of 20 people taken 10 at a time. The total number of ways to select 10 people. And what that gives us then is 18 taken 8 at a time. Anybody have their program done? Yeah. The combinations, permutations, darn. Don't worry, I think I do. Except I don't have it set up to enter numbers. I could change it very quickly. So let's do that. Go up 1. Abilities, regulations. Did I actually, because I don't need the combinations and permutations. So I will use, let me get rid of the solution part here. And I'll save this as, save as, I'll just make it proper. I'll bring this over here. So I've got, as you can see, but I do my own, I do the same thing when it comes to my permutations and combinations. I've got my binomial there, but here, what I'd say is, you know, N and K for combinations, permutations, and permutations. I'll modify it in a second to do something else. So I'm just going to enter them on the same line. Add it again here. Semicolon. Quote. There we go. And then I'll do I need some variables here. As you can see with my solution, I didn't have any variables before I got rid of all of them. So we'll have N and K. So now I'll read them in. N and K. And then what I want here is, I'm not even going to do that. That's more than finished. So combinations, probability, since this is in class, the probability of AB positive in a sample of 10 from a class of 20. And all I'll do here is I will output that. Go to the cout of my formula. So that's my probability there. Cout will be combinations, combo of 2, 2 times combinations of 18, 8 divided by combinations of 20, 10. Hopefully I didn't make too many errors there. It'll be on a line by itself. I'll just print that out. That's the fastest way to do it. But I am going to up here and over to the right place. I'm going to show you my secret sauce for trying to get all this stuff done. In class, I have bash. I use a Windows subsystem for Linux. I'll do G++. I called it prob.cpp. It gives me an a.out. program, remember your probabilities are going to be less than 1, usually. So if I leave these as integers, I'm not going to get the right answer. So I'll do a double, I'll cast here. Double, I'm having trouble typing today. And I'll do the combo there. I'll do that before I do the division. And that should solve my issue. There we go. So I've got about a 24% chance. So about a quarter of the time I'm going to get both the people that have AB positive blood. So even though they're only 10% of my entire class, if I take half my class, they're now 20% of the people yeah, those are, it makes about, it kind of makes sense about that number. So if I were to do this as a binomial, just to show you that it's a different answer, and that's why we have to count, cout, done the wrong way with the binomial hammer, we get and here I want binom, and I've got 22, pardon me, I'm taking a sample of 20, I've got a 0.2, so I've got, or 10, 2. I'm taking 10 people, I want 2 of them to have AB positive blood, and the probability for my overall population is 0.1. If I save that and run that, we'll see what the binomial would give us. As you can see, I don't like to type a lot, which is why it's always nice to have that. So here, this is a massive difference. I've got a probability of 25%, whereas the binomial tells me, oh wait, you're almost never going to get 2 people. But we know that's not the case. So that's the reason why with a small population, we cannot do that. We can't use the binomial. So with your programming assignment, that's one of the things that you'll see, hopefully. Just so you know, the sample output I give you on the programming assignment is the output that you should expect to see. So if you're solving the problem correctly, you'll get the same output I have. We can do the same thing if the probabilities are not the same. If I have a biased coin with probability of 0.6 for the heads and 0.4 for the tails, want the probability of a certain number of heads and 10 flips, can we use the Bernoulli formula, the Bernoulli trials formula? Pardon me?
I got distracted. What's the question?
Can we use Bernoulli trials for the binomial formula? I'm flipping a coin. Can I use the Bernoulli trials, or am I going to have to count? Your Father in heaven, I hope not. Actually, no, we don't. And why? We may only be flipping 10 times, but if I flip a head this time, does that change the probability of getting a head or a tail the next time? They're independent. That's the whole idea. When I'm getting people out of a small sample, a population, they're dependent on each other because we have to know something about the population typically. We know what the probability of a single individual having a particular characteristic is. But if it's independent, then I'm fine. So the answer here is yes. We can each flip is independent of the previous one. So in other words, the fact that I flip a head the first time doesn't affect whether I flip a head or a tail the next time. So each flip of the coin is completely independent of something else. So the question is, probability of getting fewer than 5 heads? Okay, this one I probably should have thought through a little bit more before I wrote it down. But it's what is it? It's the binomial of, now, if I'm flipping, how many times? 10 flips, 10 times, what's the likelihood of getting 0 if the probability is 0.6 plus the binomial of 10, 1 plus binomial of 10, well, fewer than 5 is the last one I do. 4. So I've got several of them to put together here, but at least I don't have to count them. Counting them would be a very painful kind of process here if they were dependent on each other, since it changes each time. So here, if I wanted to put this into my calculator or my program, it'd be very, very straightforward. A lot of repetitive typing. So see out the probability of fewer than 5 heads in 10 flips is see out and keep actually I could just keep the same C out going like I did above, but that's okay. Here I want binom of 10, 0, 0.6 plus, and then I like to cheat. Well, I just don't like to type a lot. No. Now, I'm willing to pay the price of having my mouse go do weird things. That. 0, 1, 2, 3, 4. Try to watch your columns, how many columns you have on stuff. Just move it down to the next line. So I've got a 1, a 0, a 1, a 2, not a 20. That would be a weird answer if I had a 20 there. A 3, a 4. And a mouse. I wish I had a mouse pad in here. That would be. I just got them to fix this so that I could use this podium Wacom rather than toting in my own all the time. And these up here, and 2 of these up here, and up to another end line down here. And that's why you use the /n rather than the end line, because it's too much typing. So we'll say, I'm really at this point just interested in what the answer is. Bang G, that's a history search. In Linux, it does a search through the command line. It says, what was the last command you typed that began with the letter G? I could make it G+, I could make it any combination of things. It just takes the string up through a blank character and says, what was the last thing you did? So it was a compilation, same thing with a dot. So I've got only a 16% chance of having fewer than 5 heads. Not very big, and it's mostly because the probability of heads is greater than 50%. We could find out what it was if it was a fair coin, too. Actually, let's do that, too. Interested now. We'll just change it a little bit here. Get rid of one of these. And we'll say probability with a fair coin. With a fair coin, here all I've got to do is change all these to 5. 5. No, I'm not. Five. All kinds of fun stuff you can do on a Tuesday. Happy Halloween. This was your trick. No treat today. Yeah, so it's a lot less than if I have a fair coin, almost 40%, 30, 35, 38% of the time, roughly. I expect to see fewer than 5. But if I've got an unfair coin, I'm down to 16%. 17%. So big difference there. So permutations, combinations program, that's the last one that we worked on. Essentially, all you're doing there, that's the one where we're looking at how many different ways can you get the first shot to emergency room personnel if I've got 12 doctors and 36 nurses. I've got to be able to tell the difference between doctors and nurses because they have different functions. But we would assume that every emergency room physician should be able to perform the functions of an emergency room physician, while an emergency room nurse should be able to perform the functions of an emergency room nurse. So I actually had a nurse practitioner do the stitches on my hand. He was pretty good though, because it was bleeding. He couldn't get the stitches weren't even, and it looked like I sewed it when I was 5. So, but no, I'm not bleeding, so it's okay. But that was the first program. Are there any questions on that program? Have you looked at the next program? Okay. Have you started either one? Okay. So I'm here to answer questions on anything that you guys might want. Let's see if anybody ever made it online. Just me. Oh wait, no, I've got somebody unknown. Unknown is on. Unknown, do you have any questions? I'm assuming that you're in this class, so I'll go ahead and assign a role for you for this class.
Oh, they're really confused.
No, they're in 2420. How is that possible? How do I have a 2420 student in? Gosh, they're in both. No, say it's not so. I think it'd be a roll in here as well. Yes. No questions? All right. Yeah?
How do you find the number of ways to administer the first dose? Because the number's like 619,580. I'm just like, I can't figure out.
Okay, it's kind of like what we did here in terms of how many ways can I select two people that from two that have AB positive blood. How did that does not affect the way I select 8 people from the 18 that don't have AB positive. So I multiplied them. It's like building a computer, doing a sandwich with different meats and breads and options there, or a pizza with different stuff like that. It's the product rule. So count the ways. How can I choose 4 doctors for the first dose?
Combination 12-4.
Combinations of 12 people taken 4 at a time. How many ways can I choose 12 nurses?
36 and 12.
Combinations of 36 taken 12 at a time. So what I then do is multiply them together. That's the number of ways I can give the first dose.
Okay. But if they were dependent on each other, would you add them?
You would have to come up with another way of doing it. I've thought about that occasionally, and it becomes too big of a problem for what we're trying to do in the class. But what if you have some married couples where the doctor and nurse are married to each other, and they need to be on the same shift? So that would then change. You wouldn't be able to do combinations because now you're changing the way that you're selecting. So with the combinations, we're still but we would have to put them into a separate group.
After it's on set.
Yeah, a different set, a different way of counting how could we make them have the same thing? And it changes now. I've got 35 nurses and 11 doctors, and then I've got this third thing, and I throw that in there. So.
Thank you. Have a good one.
Do you do the same? See you on Thursday.
See ya.